Hello and welcome to today's talk about paving the way to a native Sling. Who are we and what do we do? Well, we are Radu Cotescu, working as a computer scientist for Adobe from the Basel office. He's a member of the Apache Software Foundation and an Apache Sling PMC member, where he maintains HDL. And I'm Karl, also a computer scientist at Adobe, but working remotely from Berlin. I'm a member of the Apache Software Foundation as well, and mostly involved with Apache Sling and Apache Felix. So today's talk actually is the third talk in a series of talks that we started in 2018. In 2018 at the adaptTo in Berlin, we presented for the first time a novel approach where we bundle scripts for Sling and optionally precompile them, but then expose them via OSGI capabilities to the system. Last year, in 2019, we came back and showed how that works in a bigger picture, creating lean and mean Sling instances that lend themselves well as content renderers for distributed and remote content. Today, we're happy to report that all of this is now really integrated in the core of Sling, and we will show you how we use that in production and what we plan to do with it in the future. So regarding the current state, we integrated our approach into the Sling servlet resolver and the Sling scripting core. Together, they provide full support for packaging scripts, or in other words, resource types, into bundles. The scripts themselves can be interpreted or precompiled. At least that's true for HDL and JSP, where we implemented it. Theoretically, there's no reason that you couldn't implement it for other scripting engines, but for now, that's the tool we support. And we created special tooling to help you to create these kind of bundles. So it's on the one hand generating the required metadata, but on the other hand precompiling your HDL and JSP scripts. So in the first place, we created the scripting bundle Maven plugin. It is used to generate the provide and require capabilities that your bundle need. It should be reasonably straightforward to use it. If you package your scripts under source main scripting, then pretty much all you have to do is to add the scripting bundle Maven plugin to your POM, and it will then generate the provide capabilities for you based on the scripts that you have. If you need require capabilities, which is another way of saying if you have resource supertypes, you have to sprinkle some hints into source main scripting for that as well, but it is still reasonable, straightforward. Once you've done that, the scripting Maven bundle plugin will populate two properties, namely the provide capability and require capability property, which subsequently you can then just use in the BND Maven plugin or the Maven bundle plugin to put into headers in the manifest of the bundle. And in addition, you will need to put one additional requirement for the Sling scripting extender into your bundle so that the extender can find it at runtime and starts using it. But if you do that, you already should have a functioning bundle. However, the scripts will not be precompiled at that point. For that, depending on the kind of scripts you have to add one or two other plugins, namely for HDL, the HDL Maven plugin, which has the validate goal, which is nice because on the one hand, it validates your HDL files during build time, but also if you give it a property generate Java classes true, it will generate the Java classes during build time, and then you can just compile them with the Maven compiler and bundle them up in your bundle, and then you have precompiled HDL scripts. It sort of works similar for the JSP. We created the JSPC Maven plugin, which has a simple JSPC goal. If you put that into your POM and you have JSPs and source main scripting alongside, or just in general, your HDL, it will also compile those JSP files and package them up into the bundle as Java class. So with that, you should be all set to actually work with bundle scripts already. And how that looks concretely, we will now see when Radu shows you how we can use this approach to precompile, for example, Composo.
Thank you, Karl, and hello, everybody. Let's have a look together at what changes were required to perform in the Composum application to have its resource types served through precompiled bundle scripts. To do that, we're going to start two Apache Sling instances. On the left side of the screen, we're going to have an Apache Sling instance running the latest public release of Composum. On the right side of the screen, we're going to have a similar Apache Sling instance, but this time running snapshot builds of the Composum bundles. The snapshot builds are part of a fork that I've created in order to enable script pre-compilation. Once the instances are up and running, we're going to log in and access the system console. Let's log in. And let's log into the second instance. And as I said, let's head to the system console. Let's filter by the Composum bundles. And let's compare the package manager bundle in between the two instances. As you can see, one is a release version, the other one is a snapshot version. But I would like to focus on the provide and require capability headers. So if we look at the left side of the screen where we have the provide capability of the released bundle, we see that it describes a series of OSGI services. On the right side of the screen, however, the provide capability headers provide a new capability called Sling-supported. And its properties are the familiar Sling-supported registration properties. These were defined with the help of the scripting bundle Maven plugin that Karl has already mentioned. What the plugin does is that at build time, it looks at the file system structure of your project. And based on how you've organized your scripts, which is very similar to how you would deploy scripts in a JCR repository, it creates the provide and require capabilities. We see a list of resource types, which could potentially have selector properties, like we see here, for example. It could additionally have extensions and methods as well. Let's look, though, at the require capability header. I do know that this bundle relies on a resource type provided by the Composum Commons bundle. And this we see here in the require capability header. The first requirement that we see is the one that developers have to use in order to make sure that their bundle is going to be wired at runtime to the Sling servlet resolver. And this is the Sling scripting requirement. But if we look further at the requirements, we're going to see that this bundle requires a certain resource type to be present, namely Composum, Nodes, Console, Page Description. Without this requirement, this bundle would not be able to start. Luckily, the Composum Commons bundle is available, which provides this capability. Let's see how the application behaves at runtime, if there are any notable differences. So I'm going to go to the root page. And then we're going to launch Composum. Let's do that by clicking on the Browse Content. And I gives you notice that the application on the right side of the screen has actually loaded faster. This is because the scripts are already precompiled, and what happens at runtime is that for each precompiled script, the Sling servlet resolver automatically is going to register a servlet. The servlet is going to be backed by this precompiled script, which we call executable. And when the request kicks in, the Sling servlet resolution process is going to detect the appropriate servlet and directly access the executable. On the left side of the screen, where we have the more traditional approach with scripts deployed to the content repository, what happens is that at the resolution time, the platform is going to detect which is the most appropriate script. It's going to read it, it's going to compile it, and only after this step has been completed, the compiled result is going to be stored as a servlet in the servlet cache. So we already had some performance improvements at the first request. Let's look at the structure that the application has in the resource tree. Let's extend libs, Composum, nodes, browser. Let's do the similar thing for the other app. Libs, Composum, nodes, browser. They look the same. However, there are definitely some differences. Let's pick the browser JSP script. On the left side of the screen, the browser JSP script is a anti-file resource. It's something that we're all used to when we're writing applications for either Sling or AEM. On the right side of the screen, although we have the same node, at runtime, this is going to be presented as a servlet resource. Do you remember when I said that the scripts are going to be precompiled and then they're going to back up servlets? That's exactly what we're seeing here. We have a bundle script servlet, which acts on behalf of this script. And at runtime, when we actually access this node, we're actually going to access the executable that backs the resource type directly. Obviously, because the script is going to expect a certain context, it might very well that when you access it directly, you're not going to get what you want. But in the context of your application, things are going to work exactly like you would expect to. On the left side of the screen, if we were to access the browser.jsp resource, we would get the code that's backing the script. We'd basically get a rendering of the JCR data property on the JCR content node. And the application behaves the same no matter which part of it we would access. We would be accessing packages. We would again see how fast the one on the right loads. It's the same for users because we've precompiled all the modules. So what were the changes that were required to make Composum work with precompiled scripts? Well, let's look at the commit that I had to add. In each POM file, I had to add the scripting bundle Maven plugin. This is the one that generates the provide and require capability headers, without which the servlet resolver would not know how to automatically map servlets to your precompiled scripts. Because Composum relies on JSPs, we have the JSPC Maven plugin. The JSPC Maven plugin is going to take all the JSPs and compile them and generate Java classes out of that. One notable difference between the modules is that in this case, we had to extend the resource directories configuration and provide SRC main resources as one of the directories in which the JSPC Maven plugin has to explicitly look for files. This was needed because the Commons bundle provides a tag library definition file, which otherwise would not be read during the compile phase. And then if we look further, the configuration that we had to add to the Maven bundle plugin, we had to generate the provide and require capability headers. And for this, we rely on the pre-existing provide capability and require capability properties provided by the scripting bundle Maven plugin. In addition, we manually added this requirement, which is the Sling scripting one and the appropriate version, so that at runtime, the bundle which serves precompiled scripts is automatically wired to the servlet resolver. The other changes were trivial. We just had to move the scripts from SRC main resources, where Composum used to have them before, to SRC main scripts. The SRC main scripts is the default folder in which both the scripting bundle Maven plugin and the JSPC Maven plugin look for when they run their modules. And if we go down into the patch, we just see that similar changes were added to each module. So we have the familiar plugins together with their properties, and we just moved files around. One notable file is the extents file. This extents file tells us what the relationship is between two resource types. Before, and when we were defining the scripts in regular files, we used to add some additional metadata that would contain properties of the JCR nodes, one of which it was the Sling resource supertype property. The extents file replaces this content mapping and explicitly defines which property, which resource type we're actually extending, or basically from which resource type we are inheriting in a more correct way of defining what the process is. So if you look at this resource type, Composum nodes browser description has a Sling resource supertype property of Composum nodes console page description. And this is going to help us with the servlet registration properties. And it's going to create the hierarchical structure between them. So that was about it. The changes were relatively trivial. And for a more complex example, in the context of AEM, we're going to have a look at this in the next demo.
Right. So now that we've seen how you can use bundle scripts to even precompile something as complicated as Composum, let's talk a little bit about why doing this at all. So in the first place, the nice property of the system now is that you have much faster startup times of the whole application. That's on the one hand because we have the scripts precompiled, but on the other, they're quicker to be found. And especially, as Radu showed you, you don't even have to put the scripts into the repository, which also means leaner instances up to a point. Like we showed last year, for example, you can even run without a local repository at all and just get content from remote sources, but have your scripts work locally out of bundles. Another nice thing about this approach is that with the require and provide capabilities, we get explicit dependencies between scripts. So when you want to deploy a bundle, you will see whether it actually has the scripts it requires in the system or not. That's very helpful. And in addition, we also can version resource types. So that's nice for backwards compatibility. If you want to evolve your scripts, for example, you can start versioning them in a semantic versioning fashion, and the bundle scripts will take care of finding the highest version. And ultimately, all of this means that we can have better ahead of time verification of our systems, because as I already said, we can see whether the scripts of a bundle will resolve and all the resource supertypes are there, but also because they now use a bundle class loader, we get the real package imports so that when we build the system, we can already tell if a bundle will work or not. And last but not least, we hope that in the not so distant future, we can actually use this approach to compile Sling instances down to native images using Karl and Substrate VM. I will talk about that a little bit more later. But for now, let's talk about something else first, which is, given our background, makes some sense, namely, what about AEM? And we're glad you asked. We actually are using precompiled bundle scripts already in the context of AEM, namely in the context of AEM as a cloud service, where it is used to speed up the instances. But it's also part of the AEM as a cloud service SDK, where we have the AEM precompiled scripts bundle, which is serving all built-in scripts. In other words, the ones coming from libs that comes via precompiled bundle scripts. In addition, the resource types are, of course, also exported by that bundle. That means that you should be able to actually create precompiled bundled scripts yourself and use them in AEM as a cloud service and in the AEM as a cloud service SDK today. And so let's see how that looks like.
Thank you, Karl. So let's have a look together how we can already start using precompiled scripts on AEM as a cloud service. For this, I've prepared a project based on the AEM project archetype. I used a snapshot version of the archetype. Version 24 is going to be out soon with a lot of enhancements to support you in your way to develop projects for AEM as a cloud service. From all the modules that the archetype generates, I've only kept the ones that made sense for this demo. Namely, I have a bundle which provides my script and its associated Sling model. I have the UI apps content package, which uses the familiar proxy pattern for the core components. I have the UI apps structure content package, which makes sure that my content is going to be installed in the correct order. And I have the UI content package, which provides the skeleton of the website together with a demo page. Let's look at the component that I created. I wanted to create an image component that uses the picture tag and the source set in order to implement its responsive behavior. If you remember how the core image component looks like, the responsive behavior is implemented through a client-side script that selects the best image according to the viewport. However, I wanted to test the behavior of the browsers through the picture and source set tags. My component extends the core image component, and this is marked through this extends file. And the Sling model that I had to create for it only adds one more method to the already existing set of methods provided by the core image component, namely get source set. In the implementation, I've used the delegate pattern. On the init method of the Sling model, I create my source set, and then I return it. Everything else is based on the delegates, on the default implementation of the core image component. To pack it, I use the HTML Maven plugin to compile my code. And I've used the scripting bundle Maven plugin to generate the metadata that the bundle needs. And in the BND Maven plugin, I had to add the require and provide capability headers, as we've seen before with Composer. So let's check the project structure. If we look at the hierarchy of the components that we have, we see the image component here, which is in a custom resource type. It inherits from the core image component, but it has no script. So how does the whole rendering process work? Well, we have here a page that we've edited. I've added a carousel component, and inside we have 3 image components. Let's look how this image component actually works. So we're going to load the page, and we're going to see that the carousel is already cycling through the images. Let's test the responsive behavior of the component. So let's load again the page. And we're going to see that the images which were loaded are at their widest allowed setting, 2048 pixels. If we were to resize the browser window, let's clean the request log and refresh, we would now see that the images which were selected by the browser are at one of the lowest allowed width for 180 pixels. So how did the rendering process look like? Well, we can always check the recent requests tab. Let's refresh to make sure that we get the most recent request. And let's look at the EN page. And let's look for the image component. So as we can see, when the node with the resource type AEM adaptTo 2020 demo/component/image resource type was loaded, a bundle script servlet was used for the rendering. And that corresponds to the script that I had on my file system. As you can see, all the other scripts were actually precompiled because, as Karl mentioned before, the AEM precompiled scripts bundle is available in AEM as a cloud service and provides all the resource types from libs as precompiled scripts. What are the advantages? Again, as we mentioned before, we have explicit mentioned, require, and provided capabilities. So we would allow then the OSGI platform to correctly establish the wirings between dependencies. Alternatively, we can also introduce versioning in the resource types, which is something that we've showed in the previous 2 years. And we now are sure that when we install a bundle with scripts, that all of its requirements are satisfied. As a way to show you this and ending the demo, I'm just going to do a funny thing. I'm going to remove the precompiled bundle scripts bundle from AEM. So let's look for this bundle. I'm going to completely remove it. I'm going to refresh my packages. And I'm going to see that my bundle now is in installed state because the core image component is not available to it anymore. Thank you.
Right. So now that you've seen how you can migrate an existing body of work like Composum yourself, and also how you can use bundled scripts inside AEM as a cloud service, the question is, what are the next steps for us? Well, if you convert an existing application, there's still help that could be provided. So we want to work on some tooling for that. And especially in the context of more, backwards compatible versions of it, where you potentially still need to have the scripts and content packages to deploy in settings where bundled scripts are not around. We want to provide a tool which will take a content package, extract the scripts out of it, precompile it, and bundle it up and put it back into the content package. That you hopefully can have the two approaches run side by side in a given project. Furthermore, we want to have better build time checks available so that when you have precompiled bundled scripts in your project, you can take full advantage of the ahead of time verification that you could do. And ultimately, we want to explore, as I already hinted at, a new avenue to compile Sling instances down to native images with Karl and Substrat VM. And towards that end, you want to take advantage of a new standard, which is OSGI Connect. It's part of the upcoming R8 specification of OSGI, which already is in a proposed final draft format right now. So it's hopefully available really soon. And with it, it's possible to represent content that is outside of the OSGI framework, like jars on the class paths or JPMS modules, as first-class citizens, also known as bundles, inside the framework. That's nice because it blends the worlds together a little bit better, but also it at least makes it easier, if not possible at all, to compile OSGI-based applications to native code. We have a sub-project in Felix called Atomus, mostly done by Thomas Watson from IBM and Equinox fame, which helps as a bridge between the worlds and has example projects how to compile an OSGI application with Felix or Equinox to native code. So we want to try going down that route and compile Sling and bundle scripts into native executables, which hopefully will help with startup time even more and reduce resource consumption. So with that, we're at the end of our talk and we want to open it up for questions.